Welcome back, and now we're reaching the final steps in our very quick course on nuclear physics and applications. And today, in this class, it's a short class also, all these application classes are short. We're talking about analytical techniques that employ nuclear techniques, right? So essentially, we're talking about techniques for determining the chemical composition of stuff using nuclear physics. So one of the main ones we have, and we have here in our institute, is very strong and has been in use for many years, is neutron activation analysis. The idea is when you irradiate something with neutrons, you get radioactive, right? You get nuclear reactions that will produce radioactive nuclides, and then if these nuclides decay by the emission of gamma rays, you can measure these gamma rays, and then you will know what was the original composition of your sample, right? And provided you do some stuff, you can get even a quantitative analysis of the composition of the sample. So essentially what we have in any radiation is, right, if you're producing a radioactive nuclide, the activity of a given nuclide will be given by something like that has to do with the number of nuclei of that isotope in the target, the cross-section for that reaction, the flux, and the irradiation time, and the half-life, or in that case the decay constant, of the radioactive nuclide you produce. Now, we all know from chemistry that this is the number of nuclides of a selected isotope in a sample, right? It's the mass over the mass times the Avogadro's number times the isotopic abundance, right? And the fraction of that element in the target, or the composition, right? So if we get this, and so we get the activity, and we can relate it to the mass, to the fraction of a given element in the sample. Now, there's several ways of doing this. We have a specific course only on this, right, for postgraduate. So if you want, you can follow that course later. But essentially, what we can do with this technique. So the idea is we activate the sample using a neutron irradiation. We just pack the sample, put in the reactor, neutrons will irradiate the sample, and the many isotopes on the sample will undergo nuclear reactions and produce nuclear radionuclides, right? And then if you measure the induced gamma radiation, and why we have to measure gamma radiation, all those nuclides also decay by beta decay. But beta decay is of the energy spectrum is not well defined. Gamma decay, as we've seen in detectors, you have very narrow lines in a detector. So it's very easy to separate lines in a detector. So you get a spectrum and you say this line is from iridium, this line is from iron, this line is from cobalt, and you can quantify everything, right? So using this you can quantify the sample composition. Main advantage of this is that you can determine multiple elements at once. Unlike, for instance, if you go the other very well-known analytical techniques, many people like to use ICP-MS, right? Which is essentially mass spectroscopy. Mass spectroscopy, you can determine one element at a time. So if you want to determine 10 elements, you have to do 10 runs. Same thing goes for instance, atomic absorption analysis and other analysis. So multiple elements at once is something you get in neutron activation analysis, and generally speaking in a few other techniques like X-ray fluorescence. There's one advantage of neutron activation analysis over, for instance, X-ray fluorescence is in neutron activation analysis you can have in most techniques that do not use activation, you only determine the composition in the surface, right, or near the surface. And in neutron activation analysis, once again, the neutron, they penetrate deeply into the material, so you have, and the gamma rays escape easily, so you can determine the composition on the bulk, right? Another advantage is that samples are small amounts, meaning they are small if we think about some techniques, because of course if you take once again mass spectrometry, you usually have much less than that of mass. But then there's maybe the most important advantage here. We don't need any chemical processing. You just get the sample, you homogenize it if required. Sometimes you can do without it. So that's what they call an instrumental technique. So no chemical processing means no chemical steps, much less chemical residue produced, essentially no chemical residue produced. And you, every time you insert a chemical step, you're increasing your uncertainty at some point. It's not that easy to find yields and all that in chemical processes, so this is a great advantage. It's a very accurate method of measurement because it doesn't involve any real processing of the sample. And processing, you can always contaminate the sample somehow if you're not careful and everything. And the sensitivity is usually around micrograms per gram, parts per million. Sometimes you will see people talking about parts per billion. Yes, but that's just for the poster, because parts per billion you can reach it for, I don't know, 1 or 2 elements, maybe 3. The rest of them will be parts per million usually. Okay? So the concept, the neutron reaches a target, you capture the neutron, there's a compound nucleus, right? So, and this nucleus emits a prompt gamma. So it's a neutron gamma reaction, right? This gamma, in fact, it is produced during the irradiation. So there is a technique that uses this gamma. I'll come back to it just in a second. But the usual way to doing neutron activation analysis, you just leave this gamma and you get the radioactive nuclide, which will emit the beta particle and then decay to an excited state of another nucleus, and then you have the excess energy here, what in some classes ago I called the change of your purchase, right? So you did something and there's some change that has to be released as gamma radiation, and you measure this one, which is the decayed gamma radiation, also called delayed gamma. So this is neutron activation analysis, right? So there's some limitations here. First of all, this nucleus must be radioactive. Sometimes when you activate a nucleus absorbs a neutron, there's the prompt gamma radiation, and it reaches another nucleus that's also stable. And then there's no gamma radiation, there's no delayed gamma radiation, we cannot measure anything. This is true for several nuclides, right? This limits the detection of quite a few elements. There's also some other questions. The cross-section must be high, okay, that's quite natural. This guy here must have some decent half-life. If it's too short, you cannot measure. If it's too long, maybe it will be hard to measure if it's several years or something, but usually we can. And the other great limitation is, remember I told you most times the beta decay is followed by a gamma decay, but not every single time. Yeah, there is exceptions. Like, for instance, I told you phosphorus 32. Yes, so we cannot determine phosphorus by neutron capture analysis because you go all the way here, but then there's no gamma. This beta takes it straight here. No gamma emission, no way to determine, right? For these cases, there is a second option. We can measure this prompt gamma. Now, this is a much more difficult thing to do because if we want to measure the decay gamma radiation, the delayed gamma, we do the irradiation, and this is, you get this from the reactor a few days after the irradiation. Take it to your lab and measure it calmly with all time in the world in your lab. Or if the half-life here is a few minutes, there's a pneumatic station here. You irradiate it yourself, you get it back yourself, and you go to the lab. But still, we're talking a few minutes to do that, no problem. To measure this one, you have to measure the nucleus while irradiation is going on. So you cannot put it inside the reactor as we do. Our reactor has several, what we call them beam holes. They are ways to extract neutrons from inside the reactor pool to the outside, and then we can do it. There is a few things, practical things about it, because when we radiate inside the nucleus, we're talking about 10 to the 13th neutrons per square centimeter per second. And when we irradiate on the neutron beams, we are talking 10,000 times less neutrons. But on the other hand, these gamma radiations are all emitted during the irradiation, so there's some trade-off there. But anyway, this technique here can determine, I don't know, don't have it here, right? But you can determine most of the periodic table by the regular technique. But if you want to determine, for instance, hydrogen or phosphorus or other stuff like this, you need to do prompt gamma. So, regular neutron activation analysis, the delayed version, the one you take your sample after irradiation to your lab. It has good precision, accuracy, and sensitivity. Of course, there are techniques that may be better than it in one or the other thing, but it's very good all around, right? It's non-destructive, and I don't like the term non-destructive here because, of course, you have irradiated the sample, it's radioactive now. So, yes, it is destructive, but if you go to the technique definition of non-destructive, means you do not tamper with the sample before measuring it. So that's non-destructive. No ad hoc corrections required, because for several techniques in which you have chemical processing, you have some corrections that are I don't know, maybe hard to stand by, and it's multi-elemental. But there's a few disadvantages too. You have to be. First of all, remember it's a nuclear technique. You're looking at nuclei, not atoms. So you cannot determine chemical compounds or chemical form. You cannot say if it's iron 3 or iron 2, if it's mercury is in metallic state or methyl mercury, and other things like that. So you cannot determine molecules. So it's pretty much, you know how much of a given element you have there. No clue about the chemical form or whatever. And the other thing is, as I told you, it's insensitive to things like hydrogen, oxygen, calcium, nitrogen, phosphorus, and a few others. And this can be a limitation sometimes, especially hydrogen would be good to measure, right? Oxygen too, well, all of these in fact. The analysis of some elements may take up to a few weeks, because sometimes there's too many elements, you produce too many short-lived nuclides, so you have to measure, you do a measurement for them, and then you wait 2 weeks or 3 to measure the remaining ones. because the short-lived ones, they overpower everything and you cannot see everything, right? And another thing, okay, you require a high neutron flux. It usually takes a nuclear reactor, and not mandatory. There are some neutron generators you can find that use the DT reaction, which produces neutrons, or the DD reactions, deuterium, 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 tritium, and then you can have, but then you have fluxes that are 5-6 orders of magnitude lower than the ones we have on a reactor, but it can be done. And also we have, for instance, a system here that uses 2 americium beryllium neutron sources. What is an americium beryllium neutron source? Remember, there's a strong nuclear reaction. I told you Chadwick found out the neutron existed by using this. He had a beryllium target, and he just incided with alpha particles and noticed there were neutrons going out. Yes, we can do that. We can get americium 241, which is a very strong alpha emitter, and you mix it with beryllium, and then you have a neutron source. We have, for instance, one irradiator that uses 2 of these sources, and a bit of tweaking, we can get up to 10 to the 5th newtons per square centimeters per second, much less than a reactor, but yes, for some elements you can do neutron activation analysis on this kind of setup. Okay? Now, for prompt gamma neutron activation analysis, things are a bit different, because now we're talking real-time measurements. This is an advantage and a disadvantage at the same time. You put the sample there, and the results are in your face during the irradiation. You end the measurement, you end the irradiation, you already have your results, right? This is an advantage because it's fast, but a disadvantage because you have to have a way to be looking at your sample while irradiation, right? It's sensitive to nuclides where the reaction results in a stable or pure beta emitting nuclide. That's especially true for hydrogen and phosphorus, for instance. And there was people trying, for instance, some ideas, because as the fluxes are much lower, and at the same time the gamma radiation intensity is higher immediately, because if you produce an active radioactive isotope, all of these isotopes are produced during radiation, right? So in every single case you had a prompt gamma emitted, but the delayed gammas, which be equal in number essentially, will take several half-lives to be emitted, all of them. So you have much stronger intensity during prompt gamma NA, right? So it should be useful for instance, measuring with very low neutron fluxes in a way that you may produce very little activation. And there were people studying it for detecting drugs or explosives in luggage, because these things are very hydrogen rich. But I don't know if that went somewhere, and I really strongly doubt it will be useful somewhere, because things will become a bit radioactive, and then maybe you say, okay, there's no cocaine, no explosives, but you cannot take your bag because it's radioactive. I can put this into my mind that this would be a good thing, but who knows? People do strange stuff when they're talking about national security, so whatever. The disadvantages is, the main one is the facility. It's much more complex and much more expensive. We are finishing the assembly of one of these facilities in our labs here in our reactor. Should be operational throughout this year. It took quite a while to put together and everything, but we should have one. The other thing is that the gamma emissions are usually of high energy, a few MeV, 2 MeV, 3 MeV or something. And this means, if you remember the efficiency curve of a germanium detector. This means you're on the tail, the detection efficiency is much lower. Now, another thing that uses nuclear physics are those they call ion beam analysis, and these are quite in fashion these days. Okay, there's essentially there's workshops only devoted to it, and the idea is if you have an ion beam, a small particle which accelerator that accelerates heavy ions like hydrogen or carbon or whatever, and you just send them into your source, in your sample, there are several things that can happen, right? If you have nuclear reactions, because maybe depending on the energy of the beam, you will have nuclear reactions or you won't have. In any case, when heavy charged particles go through a sample, they will provoke a lot of disarray between electrons and atoms, and this means X-rays will be emitted. And these X-rays will be characteristic X-rays of the elements in the sample. So you can measure the X-rays and have a PIXI system, particle-induced X-ray emission, right? And by these X-rays you can know the composition of the sample. The downside, you only see the very, very few first layers of your sample. For ion beam analysis, essentially, you can only use it with very thin samples. Very, very thin. I see micron thin, right? So you can just check at the particles from the beam that are scattered here. This is RBS, Rutherford backscattering, right? And then by the angle of scattering and how much energy is lost in the scattering, you can know something about the composition of the sample too. If energy is high enough to have nuclear reactions there, then you may have gamma rays, and then you have PG, which is particle-induced gamma ray emission. And if you have nuclear reactions too, you may see nuclear reaction products, and from those you may understand what was happening there, right? There's some other things like it's a very thin sample, so sometimes you send your it's a very thin sample, remember, you send your beam and all of a sudden you may have nuclei from the sample that are emitted to the back. This is called ERDA, or energy recoil Doppler attenuation, right? And just there's many things you can do. Advantages, it's usually a particle accelerator, a small one. You can turn it on and off whenever you want, and if you tune it to avoid nuclear reactions, there's very little radiation emission here, only during operation and only X-rays, right? The problem is you have to have thin films and particle ranges is low. One advantage is that sometimes if you tune your system well, you can increase a bit you can look at the energy dispersion of these nuclei and of these nuclei, not the X-rays but the RBS and the ERDA. You can have some information about the depth profile of that element inside the source, right? And you can also tune it to have a very, very small, very, very fine beam, so you have microprobes and you can probe very specific parts of your sample. So there's a facility that does it in the Physics Institute just down here. It's called LAMFI, Laboratory for Analysis of Materials with Ion Beams, right? That's essentially, and they can do these analyses for you, most of them. It's just a case of talking. If you need that, you can talk to me or someone in our department. We know the people there and we can put everything to work. It's especially useful when you want to know something about the depth profile of some element. So, for instance, here, I'll just go quickly, but each of these small techniques have its own advantages and disadvantages, right? Uh, this is just here for you to check later. But essentially, if you combine them, you have quite a powerful tool. And they have here systems that can do even 3 of these techniques at the same time, and then do a regression and know exactly, combine the strengths of all 3 techniques to have ERDA, RBS, and Pixie, and have a very complete picture of your sample, right? So essentially that's it for this. And now get tuned, stay tuned, because now we're going to our last class, right, where we will talk about several other applications of nuclear physics in your life. Bye bye, see you later.